All right. So today, I have a full day of stuff that I want to stuff into your heads. Um, I'm going to use this table a couple of times just because it's very simple, and it makes calculations simple and easy. All right. Um, so, let's say we have a binomial experiment, and this is the probability distribution for it. Okay. Oh, people are coming in a little bit late. All right, that's fine. I think we've got almost everybody now, if not everybody. All right, great. So this is the probability distribution of some experiment. Okay, whether it be flipping a coin, or pulling marbles out of a bag and then putting them back. By the way, so I was taking a look at everybody's homework, and I think it was the way that question number one was worded. Um, there were four answers, and I'm just gonna like walk through that really quickly, like without having it in front of me. Like A was flipping a coin many times. That's definitely binomial, okay, because it's either success or failure, and they're independent events, and it's happening multiple times. Okay. The second one was pulling like a red marble or black marble out of a bag, noting the color and putting it back. Okay, so that's definitely binomial also, because it's independent, they're repeated events, and it's either black or it's red. It's one or the other. Now, if you're not replacing it, then it's not a binomial anymore, because the denominator is going to change each time you pull a marble out. Okay, so that's why replacement was important. So A and B were both binomial. C was something about people's ages or something about their height or something like that, and it definitely wasn't binomial, because it could have all different answers. It wasn't just true or false, or up or down, or success or failure. And then the fourth one was uh, denoting if people were male or female. Okay, and so it's either A or B. It's one or the other. Now, that's all the genders that they allowed for that experiment. So it was binomial. Okay. And I just think that some people only gave me one answer because they weren't looking at it as which of these were. Okay. So just wanted to get that clarified. Generally, the homework looked pretty good. I'm in the process of going through it and giving everybody comments on it. But hopefully by the end of today, we'll be able to expand our knowledge base of how to deal with binomials. So what I want to talk about today is the cumulative density function. And if you got all the way down to 13b on the homework, that was a cumulative density question. And so let's say that, this is like the number of heads. You're flipping a coin, or maybe it's a bias coin or something. You flip a coin, or you perform an experiment a whole bunch of times, and the odds of you getting 4 out of 4 is 0.4, 3 out of 4 is 0.3, 2 out of 4 is 0.2, and 1 out of 4 is 0.1. So what is the prob? And this is kind of like just a sample math to say, what is the probability of 3 or more? Well, that would be the probability of x equaling, or cap x equaling 3, plus the probability of x equaling 4. So 0.3 plus 0.4, total of 0.7. Okay, so the language is important here because you want to be able to say, you want to make sure that you say like less than or equal to, less than, greater than or equal to. And so I want to drag everyone's attention to the command Binomcdf. All right, now Binomcdf if I wanted to say, for example, if I'm going to use this table, okay, just for math life simple, stuff. If I wanted to say, and obviously this is so simple that we don't really even need the calculator for it, they're adding single digit numbers. If I said 2 or less, then it's Binomcdf. There were 4 trials, and the probability was, well, now I can't use this table because I actually have to compute this. All right, so let's do it like this. Let's flip a coin. Flip a biased coin because it's more fun. Probability of a head is 0.7. Therefore, the probability of a tail is 0.3. We're going to flip it 10 times. Now, let's find the probability of X being, of having heads less than or equal to 3. So there are 2 ways you can play this game. You could do Binomcdf, and you're going to do 10.70 plus, because that's getting it 0 times. So there's 4 scenarios that work here: 0 heads, 1 head, 2 head, or 3 heads. Don't forget the 0. Everyone forgets the 0. They just do 1, 2, and 3, and they get it wrong. Okay, and then you would do this for all right, and so this is the long way of doing it, but it would give you your answer, and it's a pain in the butt. Or you could say Binomcdf 10.73, because the CDF command is does everything underneath it. All right. Yeah. Now, if I wanted to say, and instead, the probability of X greater than 3, the way to do this is to realize that you're dealing with 4, 5, 6, 7, 8, 9, and 10. That means everything not 4 or greater. So what you do is you say 1 minus Binomcdf 10.73. Because remember, the probabilities have to add, well, if you think about it, this probability and this probability would equal 1, right? So when you're dealing with things greater than, do yourself a favor and just do 1 minus it, all right? Now, dealing with intervals is sometimes a drag, but what you would, so let's say if we wanted to do the probability of X, let's do like a probability of that, for example. Okay. You would do this in 2 pieces. You would say Binomcdf, and this would give you, this gives you 0 through 7, and then you subtract this takes off 0, 1, 2, and 3, leaving me with just 4, 5, 6, and 7, which is all we really wanted to. Okay. So when you're dealing with binomials, binomial distributions, you just kind of have to know the syntax about how you're fooling with it. All right. So if you look at that document that you pulled your homework questions out of, you'll notice that I didn't give you any of CDFs except for the very last one, because I wanted you to, I wanted to see what you would do, and how you would approach it. But tonight, what I'm going to do is I'm going to give you a couple more CDF ones that are, and I really want to see your command lines, okay, when you're putting your answers in, okay? Whatever you put up in the calculator is fine. Another thing about your homework, I don't know if I was really explicit all the time on this one, but I'm kind of like really going to be more, hard-nosed on this. Give me 3 significant digits, okay? Not 3 decimals, 3 significant digits. I certainly don't need 10. Like reading me every number on your computer, on your calculator screen, I don't need that, okay? Just give me 3 sig figs, and that's right, okay. All right, now, let's go back to my simple, silly distribution table. Okay, so the mode is 4 because it's the greatest. We need some others as well, and I want to get to those notes. So we need the mean, the median, and the mode. Okay, so the median, in this example, they're already in order, okay? And the median of this would just be the average of these two numbers because there's an even number of them. There's no difference between doing a median with probabilities and doing a median with any other data set. So the median here is the average between these two data points for up here. So the median is 2.5, not 0.25. Okay, that's a probability. We're not interested in the probability. It's the output that we're interested in. Okay, so let's say we were looking at the ages of children in a playground. Okay, and randomly, like 4-year-olds are most common in the playground. 1-year-olds are least common in the playground, but the median age in this playground is 2.5 years old. Okay, so just remember that you're dealing with the median of these numbers, not these numbers, when you're doing medians. Okay, all right, are we cool on this? Okay, I'm hoping. All right, now the mean is different when you're dealing with probabilities. This is actually called the expectation value. The expectation value is it's like the long run result of doing this experiment many times. And the way we do that is by taking the probability of a 4-year-old and a 4-year-old. So we do, it's actually this. It's it's x sub I times the probability of x equaling x sub I. Okay, and so I starts at either 0 or 1, whichever data set you start at, and it goes through however many data points there are. Okay, so in this case, it would be 1 times 0.1 plus 2 times 0.2 plus 3 times 0.3 plus 4 times 0.4. So I get 0.1, 0.4, 0.9, 1.6, and so that's 2, 3. That's 3. All right. So what I want to do today is I want to do, and we'll get into other, we'll go into variance and standard deviation in a minute. But right now, what I want to do is do a couple problems working on expectation value. Okay. So let's first of all, has everyone got this copied? Okay. All right. So I'm going to give you another data set. Okay. And so this was our coin flipping experiment that we did the other day with the biased coin. That data is actually in your notes somewhere. So first, what is the mode? Somebody just unmute, say it.
1.
Say it again.
1.
1. 1 is the mode. Now, the median, okay, so let's go ahead and sort these. So first, second, third, fourth, right? And so my median is going to be the average between these two numbers, and they come from 0 and 2. So the average of 0 and 2 is 1. Okay. So now let's deal with the mean, or the expectation value. So the expectation value is sometimes written like this. Okay, that's its notation. And so it's going to be 0 times 0.343, 1 times 0.441, 2 times 0.189, and 3 times 0.027. Okay. And when you compute all of that, it comes up with 0.9. So this is what is called a probability weighted average. Okay, because these are probabilities and it's a weighted average in the sense that this 3 only pops up this many times in my average. Okay, like if I was just averaging 0, 1, 2, and 3, I would just add them. I would add them up and divide by 4. But what I'm doing is I'm using their weights, their probabilities as weights. Okay. Whereas if I was just doing an average, 0 plus 1 plus 2 plus 3, they all get equal weight. Okay. So it's a measure. It's a measure of central tendency, like an average is, but it's a scaled average based upon their probabilities. All right. Okay. So let's play a game, shall we? All right. This is a fun one. All right. You gonna do that first? I don't know. Okay. So let's take a dartboard. And actually, I can do this nicely. And let's play a game. We have a dartboard, and it has 3 regions in it. It's got okay. Now it's got 3 concentric circles of radius 1, 2, and 3 units. So R is 1, 1. Pardon my crappy artwork, but 1. So the radius of the outer ring is 3, radius of the middle ring is 2, and the radius of the bullseye is 1. All right, now, when you throw a dart, which lands at some random location on the board because you suck at darts, the player will receive $8 if you hit the center. You will get $6 if you hit the middle, $4 if you hit the outer annulus. By the way, that's what that's called. An annulus is just the ring without. It's like, it's the middle region right here without the center. Okay, the area between 2 concentric circles. However, should you miss the dartboard altogether because you really suck, okay, you lose $7. Okay. So the probability that a player misses the dartboard altogether is 1/2. Ouch. Now, 2 questions. How will the player fare in this game? Like, are you going to make money? You going to lose money? How much are you going to win? How much are you going to lose? If you were to play this game for a very, very long time. Okay. Obviously, if you throw the dart once, you got a 50-50 chance of walking away with money or losing money. Okay. So, what is the long term result of playing? And B, the not as exciting question, but still worthwhile to know. What can you say about this game? Is it a good game to play, or is it a bad game to play? So if you were let's say, you were, doing this at a carnival or something, and you owned the carnival, is this a good game for you, or is this a good game for the customer? Okay. Will the house win, or will the house lose by keeping this game running all day long? Okay. All right. So how the heck are we going to do it? We don't have these probabilities, do we? Can we get them? How? Anyone have any ideas? So if it's a 50-50 chance of hitting the board or not, let's say, well, let's do it. what would you say? Anybody have any ideas on how to do it? By the way, why did I give you information about this if you're not going to use it? Think about it. Just think about it for a few minutes. If landing a dart here is, or anywhere in the entire circle, whatever ring it is, okay, is totally random. Which of these, by the way, do you think is going to be hit the most?
$4.
Say that again.
It's the outer.
Why?
It's bigger.
I'm not saying you're wrong. I'm just wondering why. What makes you say that?
It is very big compared to the rest.
That's exactly
Surface
right.
area.
It is the biggest. So whoever is the biggest is going to have the most hits, right? If it's totally random. So Herminio has put it in the chat. Does this have something to do with area? That is exactly right. It does have to do with area. Whoever's the biggest area is going to get hit the most, and that probability will be greatest. This will be the greatest probability. Let me instead of this, okay, so if we're having trouble putting our brain around how to do this, let's take a simpler problem and say this. This is my dartboard, okay? And I'm going to say that this is 1 by 2, okay? What is the odds of me landing in this region if I were to cut this in half? What's the probability of landing here?
1/2.
Right, 1/2, right? And why do you say 1/2?
Because it's 1/2 of the whole thing.
Okay, so if I have a total area of 2, right? This is half of it, okay? Then the probability will be half. What if I had the exact same thing, but now I change the problem? So 3/2 is here, 1/2 is there. What's the probability of landing here? Well, how much of this is there?
It would be 1/4.
Somebody is very, very quiet. Somebody said something, but it was very, very quiet. And I think it was right.
The probability would be 1/4 because you add the total area, which is 2.
Yes. Right. It is 1/4 because it's 1/4 of the whole box, right? Okay. So now, let's say I had the same problem, but now let's change it a little bit. I'm going to make a square. crappy looking square. And I say, and again, it's totally random, right? You know, it's like totally random. And this is my target. What are the odds of it landing here if this represents, if this is 10% of the area, and this is 90% of the area, what are the odds of landing here?
One-tenth.
Yeah, 10%, because it's 10% of the area, right? So now let's take this problem and let's ask ourselves, what is the probability of landing here? Okay, so I already know that I've hit the target. Okay, like you close your eyes, you throw the dart, and it hits and makes that thunk. All right, so you know you've hit the target. What are the odds of you landing here? Well, let's go back here. The odds of me landing here were 10%. The probability was of x was equal to 0.1 because it was 10% of the overall area. Okay, so the question is, what is the percentage of the overall area that's in the inner bullseye region? So how do I find that area, that percentage rather? Well, first, how do I find that area?
We need the radius, and then we need to do that pi formula.
I love it, that pi formula. What is that pi formula?
Pi r.
Like pi r squared, right?
Yeah, pi r squared. So we know its radius. We were given that. Okay. Go ahead. And well, first of all, its area, let me get some better paper here. Let's do this. Radius of the inner so the area is equal to pi r squared, which is pi times 1 squared, or just pi. Now, that is not a percentage. How do I get the percentage?
The probability of hitting it divided by that.
Well, that's what we're trying to find, is the probability. We don't know that. So what the question is, what percentage of this target is the bullseye? How do we find that percentage?
You take the area of the third circle and then divide.
Okay, so the radius of the outer is 3. So the area is pi times 3 squared, which is 9 pi. So the probability of hitting the inner is equal to the area of the inner divided by the area of the outer. So pi over 9 pi, or 1/9. Which is 0.1 bar. So now let's find the middle annulus. Take a few moments and calculate the probability of hitting the middle annulus. go ahead and put it in the private chat. Okay, most people are either getting it or they're making the same mistake that everybody else who messed it up is. The radius is 2, but I only want the purple region. I don't want the purple and the black. So the area of that outer ring is pi times 2 squared, or 4 pi, but I have to take away the inner region because I don't want that. That's a different area altogether. So, and we already know that. So we're going to subtract the inner one, which is a pi, and we're going to get 3 pi. And then we're going to divide it by the total area, which is 9 pi. So that gives me 3 pi all over 9 pi, or just 1/3. Okay. Or 0.3 bar. Okay. And now the probability of the outer would be that its radius is 3, but we want to subtract the inner one. So its area is 9 pi minus the middle one, which was 4 pi, and getting 5 pi, which is, and then we divide by the total area. So 5 pi divided by 9 pi is equal to 5/9, which is 0.5 bar. Okay. However, we're still not done. Let's go ahead and make the table. So I've got okay. So let's fill in this table. What goes here?
1/2.
So we did these probabilities already, but for my outer, my probability was 0.5 bar, right? That's more than a half. And aren't all 4 of these supposed to add up to 1? So let's kind of go back to that thinking that we had before, which was hit, miss, outer, middle, inner. This was 1/2 and 1/2. Now, the probability of hitting the outer ring is 0.5, or let's leave it in fractional form, 5/9. What about the middle? Well, that was 1/3. And the inner was 1/9. So what is the probability of landing in the outer ring? Well, 2 events have to happen. First, I have to hit, and then 5/9 of the time, it lands here. So my overall output, my real probability, is 5/18. Does that make sense? And if you were to put down 5/9 right here, or 0.5 bar, you would immediately have a problem because you would be greater than 100%. Okay, that should be a warning all the time. If your probabilities are greater than 1, you're wrong. You're just wrong. So my middle would be 1/2 times 1/3. I'm just gonna put these in there, 5/18. My middle, 1/3 times 1/2, which is 1/6. And my inner is 1/2 times 1/9, or 1/18. And just to validate the 2 people who left it as an unreduced fraction, you're not wrong. In fact, having them not have reduced fractions actually will help you here, because this is 9/18, 5/18, 3/18, and 1/18. And if you add up 9 plus 5 plus 3 plus 1, it is 18/18. So it is correct at 1. Awesome. Okay. And by the way, I was just busting your chops, both of you guys. Don't worry about it. Now, what is going to happen if you play this game all day long? Will you walk away with money? Or will you lose everything you got? And this is where the expectation value comes from. Okay? So we go back to our rules. Okay? And we realize that in each of these events, there is an outcome. So half of the time, you're going to lose $7. Okay? So if we were to look at this and say, on average, you will lose $3.50 every turn. You see? So this is 1/2 times -7. 5/18 of the time, you will win. The outer one is $4. 1/6 of the time, you will win $6. And 1/18 of the time, you will win $8. So let's go ahead and compute that, just to make our lives easy, because we don't want to bother with it too much. And you will basically lose 94 cents each turn. So, is this favoring you? Is this favoring the house? Is it fair or not?
It's favoring the house.
Right. I like this game because you're playing it and I'm not. Okay. All right. Like, this would be a good game for the not for the gambler, but for the house. So if your and so let's think about this way. A fair game is one where the expectation value is 0, where you have equal chances of winning or losing. And if you play and over and over and over again, and you do it for 100 years, you will basically break even. Okay. If it favors the player, the expectation value is positive, and if it favors the house, the expectation value is negative. Okay, so this is not a fair game. Okay. Okay. How do we feel about expectation values? Scale of 1 to 5. Okay. All right, so let's do this. Let's do another example. Or rather, you'll do this example. We take 2 regular 6-sided dice. And we roll them, and we add up the totals. Okay. So the question is, what is the expectation value? My suggestion is to make a table. And if one of your dice is a die, if one of your die is a 3 and the other one is a 1, then the total will be 4, right? So fill in this chart and then make a chart how many times. Well, first of all, what's the smallest roll, right? It would be 1 and 1. How many times does 2 show up? How many times does 3 show up? And so on and so on and so on. What's your denominator going to be for this, by the way? I'll give you the first one. It happens 2 out of how many times? What's my denominator here? How many entries are in this box? 36, right?
36.
Okay, how many times does 3 pop up? Well, it's going to pop up here, and it's going to pop up here. Well, 2 only pops up once. What am I doing? I'm an idiot. 1 out of 36. 3 pops up 2 times out of 36. And now fill it all the way up. So make this full chart, make this full chart, and then calculate your expectation value, please. When you get an answer, put it in the private chat. Okay, so almost everybody I think is done. So the answer is 7. Okay, and we see that happening, there. And if we were to think about this in the long run, the most likely roll over time, the average roll is going to be 7, because there are so many ways of getting a 7. Okay, 6 and a 1, 5 and a 2, and so on. Okay, so let me ask you this question. Let's say there was a game and the player has to pay $8 to get the dice, and he wins $1 for every point on the dice total. So if he rolls the die and he gets a 2 and a 3, he would win $5. Okay. What would the expectation value be in a game like that? It costs you $8 to get the dice in your hand. And then you roll them and you get how many points there are. You don't need to recompute anything.
So if it takes $8 to get the dice, you said, right?
Correct.
You roll them, and whatever added up
Is
the
what
points, that is in dollars that you
Correct.
get back.
Correct.
If our average or expectation value is 7, so on average we would get 7. But if we have to pay $8 each time, that means we're losing.
Right. You lose $1 every roll on average. Okay. Okay. So good. Yes, you're losing it because on average you get 7, but you also pay 8. So yes, you lose $1 in the long run. Now, here's another game. A player pays $8 for the 2 dice. Okay. And if 2 6s show up, what are also known as boxcars. Okay. I don't know if you guys play. No one plays craps anymore. If 2 6s show up, the player wins $252. And 0 everywhere else. Is it more profitable or less profitable? What is the expectation value for this one?
I would say you'd still lose.
Well, it's kind of scary, right? I mean, everything that you roll, you get nothing. But if you nail those 2 6s, man, you're walking out of there $252 more, that's pretty good.
Yeah.
It's scary. So we're just about out of time, so I wanted to throw this at you. The idea here is you have to compute the expectation value, right? And if you do the expectation value with the chart information that you already got, you get nothing for every roll except for the last one. And 252 divided by 36 is 7. So on average, every roll you would win $7 on average. But you're still paying $8 to play the game. So you're still losing $1. So the expectation value here is negative $1. So both games suck. And they suck as much as the other one does. Because you're still overall losing $1. Unless you're really lucky and you roll a boxcar, you take your money and you go home. Okay. How are we doing so far? Are we okay on this? Okay. All right. So I will send you a document via email again on doing expectation values, and I'll probably have you use that same I'll assign you some problems about Binomcdf out of the document I sent you last time. Okay. But you know, CDF is not that bad, really. I mean, it's much like doing PDF. It's just knowing how to put it in the computer. But I'm going to give you some problems on expectation value that I'd like you to do. Okay. All right. Everyone have a wonderful day. I will see you all on Thursday. Go out and play in the snow.
Have a good one.
See you guys.
You have a good one.
Mr. Uncle, if you have a quick second, I had a question kind of similar to this.
Okay, hold on one second. Pablo, you got a question?
It's not important, so if you
No,
don't
it's
have
okay.
time, it's not like